The Hubble Space Telescope's camera freezes. On the monitors inside a control room in Baltimore, astronomers stare at something that defies everything they thought they understood about the universe. A perfect arc of blue light bent into the shape of a horseshoe, wrapped around an ancient orange glow. For 18 years, they thought they knew what they were seeing. A beautiful example of gravitational lensing. A cosmic optical illusion created by the warping of space-time. A curiosity worth studying, but nothing more. They were wrong. Hidden inside that orange smudge, invisible to every telescope ever pointed at it, silent in every wavelength of light, and completely dormant for what might be billions of years, is a gravitational monster so massive it approaches the theoretical limit of what the universe should even allow to exist. 36 billion times the mass of the Sun, all of it packed into a region smaller than the solar system, a point in space where gravity is so intense that nothing, not light, not information, not hope, can ever escape. And when the international team of researchers finally measured what was lurking there, they realized they weren't just looking at a black hole. They were looking at what happens when an entire galaxy cluster dies. 5 billion light-years away, in the direction of the constellation Leo, there is a smear of light that astronomers have been puzzling over since 2007. They call it the Cosmic Horseshoe, and from Earth it looks like a cosmic question mark hanging in the void. The horseshoe itself is a nearly complete ring of pale blue light curving around a central blob of orange. It's beautiful, ethereal, and completely impossible unless you understand the physics that created it. But here's what doesn't make sense at first glance. That horseshoe-shaped arc, it's not actually shaped like a horseshoe at all. It's a perfectly round galaxy located even further away than the orange blob in the center, but something so massive sits between Earth and that distant galaxy that it literally bends the fabric of space-time itself, warping and stretching the background galaxy's light into that distinctive curved shape. This phenomenon is called gravitational lensing. Albert Einstein predicted it over a century ago as a consequence of his general theory of relativity. Mass tells space-time how to curve, and curved space-time tells light how to travel. When enough mass concentrates in one place, light doesn't travel in straight lines anymore. It bends, it stretches. It creates cosmic mirages that can magnify distant objects, duplicate their images, or smear them into rings and arcs. Einstein himself doubted anyone would ever observe this effect directly. He thought the alignments required would be too rare, the distortions too subtle. He was wrong. Today, gravitational lensing is one of the most powerful tools in modern astronomy, allowing scientists to see galaxies that would otherwise be far too faint to detect and to map the distribution of invisible dark matter across the universe. The Cosmic Horseshoe is one of the most spectacular examples of gravitational lensing ever discovered. The arc is so nearly complete, so perfectly curved, that astronomers knew immediately the foreground object creating this distortion had to be extraordinarily massive. And it is. The foreground galaxy, the orange blob at the center, is 100 times more massive than the entire Milky Way. It's classified as a luminous red galaxy, an ancient behemoth composed almost entirely of old red stars. No new stars are being born there. It's a galactic fossil, a relic from an earlier era of the universe. But here's where the story takes its first unexpected turn. That massive galaxy, it was only the beginning of the mystery. Because a team of researchers at the Federal University of Rio Grande do Sul in Brazil were not studying the Cosmic Horseshoe to learn about black holes. They were not even thinking about black holes. They were hunting for something far more elusive. Dark matter, the invisible substance that makes up roughly 27% of the universe's total mass and energy. Dark matter does not emit light. It does not absorb light. It does not interact with normal matter except through gravity. The only way scientists know it exists at all is by watching how it affects the things they can see, how it bends light, how it influences the motions of stars and galaxies. And gravitational lenses like the Cosmic Horseshoe are perfect laboratories for studying dark matter distribution. By carefully analyzing exactly how the background galaxy's light is distorted, astronomers can map where the mass is concentrated in the foreground galaxy, including the dark matter that cannot be directly observed. Therefore, the team pointed some of the most powerful instruments ever built at the Cosmic Horseshoe. They used the Hubble Space Telescope to capture exquisitely detailed images. They used the Very Large Telescope in Chile, with an instrument called MUSE, the Multi-Unit Spectroscopic Explorer, to measure the velocities of stars in the foreground galaxy's core. They expected to find a standard distribution of dark matter. What they found instead made them question their instruments, and that is when the data stopped making sense. Stars near the very center of the foreground galaxy were moving at velocities that seemed impossible, almost 400 kilometers per second. To put that in perspective, that is fast enough to travel from New York to Los Angeles in about 10 seconds. Fast enough to circle the entire Earth in less than 2 minutes. Something was whipping those stars around at tremendous speeds, something invisible, something concentrated in a space so small that it should not be able to contain that much gravitational pull unless it was incredibly, impossibly dense. Meanwhile, the team noticed something else in the Hubble images that previous studies had overlooked. There was not just one background galaxy being lensed. There was a second, even more distant source, and one of its distorted images appeared remarkably close to the very center of the foreground galaxy. This was crucial. In gravitational lensing, the closer a lensed image appears to the center of the lensing mass, the more precisely astronomers can measure what is causing the distortion. It was as though the universe had handed them a magnifying glass pointed directly at whatever was hiding in the galaxy's heart. The team had detected the black hole's effect in 2 distinct ways. It was altering the path that light takes as it travels past the gravitational well, and it was causing the stars in the inner regions of its host galaxy to move at extreme velocities, almost 400 kilometers per second. According to Professor Thomas Collett of the University of Portsmouth, one of the study's authors, combining these 2 measurements left no room for doubt. 2 independent lines of evidence, 2 completely different measurement techniques, and both of them pointed to the same impossible conclusion. The math only worked one way. There had to be a supermassive black hole at the center of that galaxy, but not just any supermassive black hole, not the kind that sits at the center of the Milky Way, impressive as that one is. When the researchers combined their gravitational lensing measurements with their stellar velocity data and ran the calculations, they got a number that made the entire team pause. 36.3 billion solar masses. Let that satisfying terror sink in for a moment. The black hole at the center of the Milky Way galaxy, the one called Sagittarius a star, the one that earned Reinhard Genzel and Andrea Ghez a Nobel Prize for proving its existence, has a mass of about 4 million times the Sun. That already makes it a supermassive black hole, a cosmic giant that would take light itself about 25 seconds to cross from one side of its event horizon to the other. The black hole in the Cosmic Horseshoe is 10,000 times more massive than that. Think about that ratio for a moment. If Sagittarius A star were a basketball, the Cosmic Horseshoe black hole would be a sphere large enough to contain a small town. The difference in scale is so extreme that astronomers have had to invent a new classification. This is not merely supermassive, it is ultramassive, a category reserved for black holes exceeding 10 billion solar masses, the true titans of the cosmic zoo. If someone placed this monster at the center of the solar system, its event horizon, the point of no return beyond which nothing can escape, would extend past the orbit of Uranus. Neptune and Pluto would be swallowed whole, locked forever inside a prison of infinitely curved spacetime. The entire inner solar system, including Earth, would exist within the event horizon, though there would be no way of knowing it. From inside a black hole this large, the tidal forces near the event horizon would be surprisingly gentle. A person could fall in without being torn apart, but no message could ever be sent back. No escape would ever be possible. Everything would simply drift inward toward whatever unknowable fate awaits at the singularity. But here is what made this discovery even stranger, even more unsettling, even more scientifically revolutionary. This black hole is completely silent. It is not actively feeding. There is no superheated accretion disk of gas spiraling into its maw, glowing with the fury of a trillion suns. No relativistic jets of particles screaming away from its poles at nearly the speed of light. No quasar beacon visible across the observable universe. It is dormant. Asleep. A sleeping giant that has not consumed a significant meal in what might be hundreds of millions of years. Lead researcher Carlos Melo, a doctoral candidate at the Federal University of Rio Grande do Sul, emphasized that this discovery was made for a dormant black hole, one that is not actively accreting material at the time of observation. Its detection relied purely on its gravitational pull and the effect it has on its surroundings. The black hole betrayed its presence only through gravity, through the subtle bending of starlight, through the frantic dance of stars caught in its gravitational grip. Without those telltale signatures, no one would have ever known it was there. And that raises an uncomfortable question that has been keeping astronomers awake at night ever since this discovery was announced. How many more of these cosmic monsters are hiding in the darkness, invisible, silent, waiting to be found? 36 billion solar masses is an almost incomprehensible number, but here is the question that makes this discovery truly significant. How big is too big? Because physics places a hard ceiling on how massive black holes can grow. And this discovery is pushing right up against that theoretical limit. Here is the problem, and it is a problem that goes to the heart of how black holes actually work. Black holes grow by consuming matter. Gas, dust, and unfortunate stars that wander too close. Anything that crosses the event horizon adds to the black hole's mass. But that matter does not just fall straight in like water down a drain. Conservation of angular momentum prevents that. Instead, the infalling material spirals around the black hole, forming a flattened structure called an accretion disk. And that accretion disk has a speed limit. As matter in the disk spirals closer to the event horizon, it moves faster and faster, heated by friction to temperatures of millions of degrees. But there is a boundary called the innermost orbit, the closest distance at which matter can orbit the black hole without inevitably plunging past the point of no return. Inside that boundary, stable orbits are impossible. Everything falls in. Now here is the catch that creates the theoretical mass limit. As a black hole grows more massive, it pushes that innermost orbit further and further out from the event horizon. But there is another boundary that matters, something called the self-gravity radius. This is the distance at which the gas in the accretion disk becomes more attracted to itself than to the black hole at the center. When a black hole becomes massive enough that its innermost orbit exceeds its self-gravity radius, something catastrophic happens to the feeding process. The accretion disk becomes unstable. Instead of funneling gas into the black hole, it fragments. It collapses under its own gravity. It forms stars. The black hole essentially chokes on its own food supply. It cannot grow anymore through normal accretion. Back in 2015, Professor Andrew King at the University of Leicester calculated exactly where this limit should kick in. His answer was somewhere around 50 billion solar masses, depending on how fast the black hole is spinning. So a black hole weighing 36 billion solar masses is not just impressively large. It is approaching the maximum size the universe should theoretically allow through normal feeding processes. But that calculation assumes the black hole only grew by consuming gas and dust. What if there is another way for black holes to reach such monstrous proportions? This is where the Cosmic Horseshoe becomes truly fascinating, and where its classification as a fossil group changes everything astronomers thought they understood about how the largest black holes in the universe came to be. A fossil group is not just a single galaxy. It is what remains after an entire galaxy cluster cannibalized itself over billions of years. Picture this. Around 10 billion years ago, in a region of space that would eventually become the Cosmic Horseshoe, there was not a single massive galaxy. There was an intense cluster, perhaps dozens of galaxies, each with its own stars, its own dark matter halos, and its own supermassive black hole at the center. These galaxies were gravitationally bound to each other, orbiting around their common center of mass. But gravity is patient, and gravity is relentless. Over billions of years, the galaxies began to interact. They passed close to each other, their mutual gravity raising tidal distortions. They stripped stars from each other's outer regions. Their dark matter halos began to overlap and merge. Eventually, the galaxies themselves began to collide and combine. Not in violent explosions, because the stars within galaxies are so widely separated that actual stellar collisions are vanishingly rare. Instead, they engaged in a gravitational dance of merger and absorption. As the galaxies merged, so did their central black holes. This is key. When two galaxies collide, their supermassive black holes do not immediately find each other and combine. First, they sink toward the center of the merged galaxy through a process called dynamical friction, essentially gravitational drag caused by interactions with surrounding stars. This process can take hundreds of millions of years. Eventually, the two black holes get close enough to form a binary system, orbiting each other at the center of the merged galaxy. They spiral closer and closer, losing energy to gravitational waves, ripples in the fabric of space-time itself. And finally, they merge, combining their masses into a single, larger black hole. Now imagine this process happening not once, but dozens of times over billions of years. Each galaxy that falls into the growing cluster brings its own supermassive black hole to the feast. Each merger adds mass to the central monster. According to Professor Collett, it is likely that all of the supermassive black holes that were originally in the companion galaxies have also now merged to form the ultramassive black hole detected in the study. The Cosmic Horseshoe represents the end state of galaxy formation and the end state of black hole formation. The Cosmic Horseshoe is not just a galaxy, it is a graveyard, a memorial, the final resting place of an entire galaxy cluster that consumed itself over cosmic time, leaving behind only this single massive remnant and the sleeping monster at its heart. If that interpretation is correct, then 36 billion solar masses is not just a measurement of how much matter fell into this black hole. It is a census. A record of every supermassive black hole that ever existed in that ancient galaxy cluster, now merged into a single incomprehensible entity. And here is the part that might keep a person awake at night. This process of galactic cannibalism is not unique to the Cosmic Horseshoe. It is still happening all across the universe. Right now, the Milky Way galaxy is on a collision course with its nearest large neighbor, the Andromeda galaxy. For decades, astronomers believed this merger was inevitable. Measurements of Andromeda's velocity showed it approaching at roughly 110 kilometers per second. Calculations suggested the collision would begin in about 4 to 5 billion years. The two spiral galaxies would spend billions of years tangling together, their graceful spiral arms distorting and eventually dissolving as their stars mixed. The end result would be a single giant elliptical galaxy that astronomers have already nicknamed Milky-Way-Andromeda, or sometimes Milk-Dromeda, depending on who you ask. And at the center of that chaos, two supermassive black holes are spiraling toward each other. One is Sagittarius A star, weighing in at 4 million solar masses. The other is Andromeda's central black hole, somewhere between 100 million and 200 million solar masses. According to detailed simulations published in 2021, after the galaxies finish merging, roughly 10 billion years from now, those two black holes would orbit each other in an ever-tightening dance. The final stage would happen relatively quickly in cosmic terms, perhaps 17 million years from the galaxy merger to the black hole merger. In those final moments before they combine, the two black holes would radiate gravitational waves with the power of 10 quintillion suns, a cosmic scream that future gravitational wave detectors, such as the LISA mission, might be able to detect from similar mergers happening elsewhere in the universe. But here's the twist that no one expected, and it came from a study published just this year. Using the most precise measurements ever made by the Hubble Space Telescope and the European Space Agency's Gaia mission, a team of researchers recalculated the probability of the Milky Way and Andromeda collision. They accounted for factors that previous studies had simplified or ignored, particularly the gravitational influence of other nearby galaxies like the Large Magellanic Cloud and the Triangulum Galaxy. Their conclusion was startling. The collision is not inevitable. There is roughly a 50-50 chance that the Milky Way and Andromeda will swing past each other without merging, at least for the next 10 billion years. The galaxy might dodge its fate entirely, but the Cosmic Horseshoe was not so lucky. Its galaxy cluster merged long ago, billions of years before the light astronomers are seeing today even began its journey toward Earth. And what remains is a warning. A glimpse of what maximum cosmic destruction looks like when gravity has its way. So why should any of this matter? Why should anyone care about a dormant black hole in a distant galaxy impossibly far away, utterly beyond human reach or influence? Because this discovery reveals something profound about the relationship between black holes and the galaxies they inhabit, a relationship that turns out to be far more complex and mysterious than scientists previously understood. For years, astronomers have observed a remarkably tight correlation in the nearby universe. Bigger galaxies host bigger black holes. More specifically, the mass of a galaxy's central black hole seems to scale with the velocity dispersion of stars in the galaxy's core, how fast those stars are moving on average. This relationship is called the M-sigma relation, and it has been confirmed in galaxy after galaxy. The correlation is so tight that it suggests black holes and their host galaxies somehow grow together, their evolution intertwined through feedback processes that scientists are still working to understand. When a black hole feeds actively, it can heat the surrounding gas and blow it out of the galaxy, shutting down star formation. When star formation proceeds rapidly, it can funnel gas toward the center, feeding the black hole. It is a cosmic dance of mutual regulation, but the Cosmic Horseshoe black hole breaks this pattern. It is too massive for its galaxy. It sits roughly 1.5 standard deviations above where the M-sigma relation says it should be. Something unusual happened during its formation, something that decoupled the black hole's growth from its host galaxy's evolution. Maybe the merger process that assembled this monster followed different physics than the gradual coevolution seen in normal galaxies. Maybe the galaxy lost significant stellar mass during its violent history, while the black hole retained everything it ever consumed. Maybe ultramassive black holes simply do not follow the same rules as their smaller supermassive cousins. The research team noted in their paper, published in the monthly notices of the Royal Astronomical Society, that this deviation at the massive end likely reflects distinct evolutionary pathways during the formation and assembly of these galaxies. In other words, astronomers are seeing something new, something that challenges existing models, something that forces them to ask whether everything they thought they knew about the largest black holes in the universe might be incomplete. And there is another reason this discovery matters, a reason that goes beyond pure scientific curiosity. This was not supposed to be possible. Measuring the mass of a dormant black hole 5 billion light-years away is, by conventional methods, essentially hopeless. When a black hole is not actively feeding, it does not announce its presence. It does not glow. It does not emit radiation across the electromagnetic spectrum. The only way astronomers typically measure distant black hole masses is by studying active galactic nuclei, black holes that are gorging on gas and shining like cosmic beacons. But the technique used here, combining gravitational lensing analysis with stellar kinematics, changes everything. It means scientists can weigh sleeping giants. They can find the monsters hiding in the dark. According to Carlos Mello, what makes this discovery particularly exciting is that this method allows astronomers to detect and measure the mass of these hidden ultramassive black holes across the universe, even when they are completely silent. This opens a new window onto the cosmos. Because if ultramassive black holes can hide in plain sight for billions of years, detectable only by the subtle gravitational fingerprints they leave on their surroundings, how many more are out there? How many dormant behemoths are lurking in the centers of distant galaxies, invisible to every survey ever conducted, shaping their cosmic neighborhoods from the shadows? The European Space Agency Euclid Telescope, launched in 2023, is surveying billions of galaxies looking for gravitational lensing events. NASA's James Webb Space Telescope can peer deeper into the universe than any instrument before it, studying galaxies from the earliest epochs of cosmic history. The upcoming extremely large telescope, currently under construction in Chile, will be able to measure stellar dynamics with unprecedented precision, even in galaxies billions of light-years away. The researchers who discovered the Cosmic Horseshoe black hole believe their work is just the beginning. There are thousands of strong gravitational lenses already known in astronomical catalogs. Many of them likely host dormant ultramassive black holes that have never been measured. Astronomers just never knew how to look for them before. Now they do. And the universe may be full of sleeping monsters they've only just begun to wake. The Cosmic Horseshoe sits 5 billion light-years away, a silent memorial to a galaxy cluster that consumed itself across billions of years of cosmic history. At its heart, a black hole, 36 billion times the mass of the Sun, waits in perfect darkness. Not growing, not feeding, just existing at the ragged edge of what physics allows, holding the compressed remains of perhaps dozens of smaller black holes that merged across the ages, a gravitational tomb for an entire cluster's worth of cosmic evolution. It took 18 years from the Cosmic Horseshoe's discovery for anyone to realize what was hiding there. It took the combined power of the Hubble Space Telescope and the Very Large Telescope. It took two completely independent measurement techniques, gravitational lensing and stellar kinematics, pointing to the same impossible conclusion. And it took a team that wasn't even looking for black holes in the first place. They were searching for dark matter. They found something far more extraordinary. But here's what keeps astronomers staring at their screens long after everyone else has gone home. If this black hole has been hiding for billions of years, silent, invisible, massive beyond human comprehension, detectable only by the gravitational wounds it carves into the space-time around it, what else is out there that hasn't been found yet? The universe is nearly 14 billion years old. Galaxies have been merging and colliding since before the Earth existed, since before the Sun ignited, since before the heavy elements in human bodies were forged in ancient supernovae. Scientists have been looking up at the night sky with instruments for less than a century. They've been capable of detecting gravitational lensing for only a few decades. Space telescopes have existed for about one human lifetime. In that brief window, humanity has discovered that the universe is far stranger and more violent than anyone's ancestors ever imagined. Black holes weren't even accepted as real physical objects until the 1960s. The first direct image of a black hole's event horizon wasn't captured until 2019. And now, just a few years later, astronomers are finding dormant monsters that dwarf everything they thought they knew about cosmic extremes. What has been found so far is extraordinary. But it's almost certainly just the beginning. Somewhere in the dark, between the galaxies, in the hearts of ancient fossil groups that haven't yet been discovered, more monsters are waiting. And now, for the first time, astronomers know how to find them.